Okay, we're going to look at another way of finding a volume by revolution. And this is typically, though not exclusively, for when you're rotating something around the y-axis. So let's imagine that we have some shape. Let's say the shape looks like this. And we want to rotate that area around the y-axis. Well, if we do that, um, the way that we're going to think about that is we're going to think about that once again as taking a little bit of a strip. So here's our strip, and it has height f of x, and a little bit of width d of x. And when we wrap this around the y-axis, what we're going to create essentially is a cylindrical shell. So our cylindrical shell will look like that. And it will have a little bit of width to it, and a little bit of width will be dx. That's this little kind of substance to it, thickness, I guess, of it. And it has a height of f of x. And then, since it's a cylinder, we're going to be talking about its radius. So its radius here, that radius x, since we're rotating it around the y-axis, that radius x is this value right there. That's that radius x. So the visualization uh, of this shell is that if we were to unwrap it, so it's circular, and if we were to kind of cut it down the line here, so take scissors, let's see if I can pretend to make scissors. Oh, Jesus. Let's try that again. Mm, I can't draw scissors, but say we cut this. What we're going to end up making is essentially a sheet of paper now. Where that thickness is dx, and the height is f of x, and the length is the area around that circle, which is 2 pi x. So this little bit of volume, dv, the little bit of volume from this one strip equals 2 pi x times f of x times dx. And then what we're going to do is we're going to add up all of the strips over the region that we're interested in. So we're going to integrate that little d volume from A to B. And that'll get us the volume using the shell method. Now let's look at this very helpful picture of what's going on. I think this will give us some great clarity. So we can see here that the shape is being split up. And now we're going to take that and give a nice visualization of rotating that one strip around the y-axis. And we can see much better than my picture that you create this cylinder, or a cylindrical shell rather. So now what we're going to do is imagine taking all of those little strips and rotating it around. Now we're just going around half of the halfway so that we can get a better picture of what's happening. So we can see a cross section of it. Now as we fill in that, we see what our volume is going to look like. So as we rotate that entire surface around the y-axis, we get something that looks like this. It's, what is it, like a one of those cakes with the middle out of it, a bunce cake, I think it's called. So that's what happens. We split up our section into little rectangles like we've been doing. We're going to imagine rotating one of those rectangles around the y-axis, and the volume of each of those rectangles is 2 pi x times f of x times dx. And then we're going to add up all of those little cylindrical shells as we rotate them around. Being able to visualize what's going on and being able to really kind of grasp the idea behind the formulas is going to be critical for your understanding of this topic. Okay, so we've already seen this. Let's move on. The visualization they gave is significantly superior to the one that I gave, but I'm okay with that. So here's another picture, kind of looking from the top down, the idea of taking our curve here, and we're rotating that one little sliver here, and we're rotating it around the y-axis. And the idea, the hope from this image is that you get a very strong picture that by rotating it, the result is a cylindrical shell. And the little bit of volume from that cylindrical shell is the circumference. So it's the circumference, which is 2 pi r, where r in this case is determined by its x value, times the height, and the height is determined by the y value, or f of x, times the little bit of depth that it has, dx. So let's imagine, let's say that we wanted to find the volume of y equals x squared as we rotate this from 0 to, let's say, to 3. So we want to take this whole region and rotate it around. Now, what's that going to look like? Well, if this is the y-axis, we're going to get a reflection across the y-axis. And then this is going to fill in all the way around. So it's going to be kind of hollow on the inside, something that looks like that. So if we wanted to find that volume, what we're going to do is we're going to integrate. Well, we want to go from 0 to 3, so from 0 to 3. And the formula is, well, it's very formulaic. 2 pi x. And what that's doing is that's giving me the distance around the edge, the circumference, times the height, so times f of x, and in this case f of x is x squared, because my y values are always x squared, times dx. Okay, well, now we just integrate. So 2 pi x cubed, simplifying it first, and we get 2 pi x to the 4th over 4 from 0 to 3, and we know how to evaluate that. We just plug the 3 in. We're going to get pi times 3 to the 4th over 2, which is 81 halves pi. So that's the volume of our region. So we'll just look at a couple more examples of using this. And this is another method for finding the volume by rotation. So here's our general equation when you rotate it around the y-axis. It's going to be 2 pi x times f of x dx. It's integrated from a to b. In general, not around the y-axis, but in general, it's just going to be our radius times our height times our thickness. So to look at an example where we're not following just the traditional around the y-axis, you could also think about rotating some curve, and let's think about like cosine of x, and we want to rotate this section of cosine x from 0 to pi over 2, and instead of rotating it around the y-axis, let's rotate it around the x equals -1 axis. Well, what is this going to change? It doesn't change my dx, and it doesn't change my height. What it changes is my radius. So my radius is going to change here. It's clear that my radius has gotten bigger. It's gotten bigger by, as opposed to going around the y-axis, it's now increased by +1. Even though there's the -1, my radius has gotten bigger by 1. So when we rotate this sliver around that axis, it's going to have a bigger radius. So we need to accommodate that. So the volume will equal 2 pi integral from 0 to pi over 2. And what will my radius be? Well, now it's x plus 1 times my height times dx. And for most of these problems, oftentimes we're not even going to ask you to evaluate the integral. You know how to evaluate integrals. Instead, the tricky part is figuring out how do we set up the integral. So that's where the thinking exists. So let's think about another shape. We've got the graph y equals 1 minus x squared, square rooted. And just to be really clear, if we were to square both sides and then move the x squared over, what we have is an equation for a circle with radius 1. Okay, great. Well, when you do the whole square rooting, then we just get the half circle, and so that's what this is here. So the idea is if we rotate this shape around the y-axis, that two-dimensional circle is going to become a three-dimensional semisphere, half of a sphere. Well, let's do that. So really, because of the symmetry, we're only going to look from 0 to 1, because when we rotate this shell around, it'll show up there as well. So we only need to look at the first quadrant. So what we're going to look at is the integral from 0 to 1 of 2 pi times my radius, which is always x, times my height. And my height is 1 minus x squared dx. Well, while in the last example I said we typically don't integrate these, we're going to integrate this just for A, to show that we get an equation for a sphere, and B, because it's an interesting review of reverse chain rule, or the U substitution. So we notice that, let's actually move this 2 back inside, and let's make that negative and a negative. So now this is the derivative of the inside. this negative 2x is the derivative of the inside. So what we're left with is negative pi. So this is the only part we need to integrate then. 1 minus x squared to the 3/2, and then times 2/3 to accommodate, to cut that off. And that integrates from 0 to 1. So when we plug things in, we're going to get negative pi times 2/3 times 0 minus pi times 2/3 times 1 to the 3/2. The minus and the minus will go away. And we get left with just 2 pi over 3 as my volume. So this piece might have been a little bit confusing. If it was, try doing a U substitution to make that clear. If it's still not clear, get some help from me or from a peer on how to do that integration. That should be something that you can do at this point. But we get this volume here, and just to make sure that makes sense, we know that the volume of a sphere is 4/3 pi times r cubed. Well, in this case, r is 1. So the volume of a sphere would be 4/3 pi, but half of a sphere would be 2/3 pi. And we see that that answer makes sense given that that's the answer that we got. Okay, this is a really helpful little video for you to view afterwards. There's a link after this. There's a link on the Moodle site that will bring you to this video, but it's really worth watching. So I want to do just maybe 1 or 2 of these problems with you, and then that's it. So it says the graphs of the given equations bound a region in the plane. Use the shell method to find the volume of the solid generated when the region is rotated around the y-axis. So let's look at the first one. Sine of x looks like that, and it's enclosed by sine of x, y equals 0, x equals 0, and x equals pi. So we're rotating that region around the y-axis. So for for 2 rather, our integral is 2 pi times x times sine x. And remember, you need to know what these things are. The 2 pi x is the circumference, the sine x is the height, and the dx gives us the width, and we're going from 0 to pi. And that's all. What about this one? Well, we've got 1 over 1 plus x squared. What does that graph even look like? Well, if you think about it, when x equals 0, y equals 1, and the bigger x gets, the smaller y gets. And because of that x squared, you're going to have some symmetry on the other side. So it's going to look something like that. And we're looking at the region bounded between x equals 0, x equals 1, and y equals 0. So x equals 0, x equals 1, and y equals 0. So that little area there, we're rotating it around the y-axis. So we're going to get the integral of 2 pi x times 1 over 1 plus x squared integrated from 0 to 1. And I think what's important for you to start developing is an idea of which integrals can you definitely integrate by hand and which integrals is there no way for you to integrate by hand. So for right now, this would be a very challenging integral for us to solve. But this one here, not only is it very doable, but it's a fun integral to solve. So let's go ahead and do it. We could rewrite this, putting the 2 inside, as 2x over 1 plus x squared. And writing it like that, the bells that should be going off in your head are ln, 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 because we've got a function on the bottom and the derivative up top. So therefore, this equals pi times ln of the absolute value of x evaluated, sorry, of not of x, but of 1 plus x squared. Evaluated from 0 to 1. So this ends up with pi times ln of 2 minus ln of 1. We know ln of 1. What is it? I can't hear you. It'd be weird if I could hear you. We know that that's 0. So therefore, our final volume here equals pi times ln 2. And I'm not going to do those other two because there's ample other examples out on the internets if you need some more help. But that's our introduction to um, to volumes by the shell method. And I just want to end by going back to this demo that we started off with. And let's get that going. So again, it's important that you understand the theory behind this method, that we're creating a bunch of infinitely thin cylindrical shells, and we're going to add up the volume of each of those cylindrical shells as we rotate it around the y-axis, or really any other axis. And that's what we got. Thank you for viewing.